the scalp. And then it records a mixed signal from multiple brain regions at the same time. And it also includes non-neural signals like eye blinks or muscle activity, making the raw signal very hard to interpret. But after lots of processing, we look at different frequency bands. So that's on the top left or on the top right. So the theta band is 4 to 7 hertz, which is attention, cognitive control, and error monitoring. Alpha is 8 to 12 hertz, which is sensory processing and inhibition. Beta is 13 to 30 hertz, which is motor control and postural regulation. And gamma is above 30 hertz, which is higher level processing. And because these signals are so mixed, researchers use a very long, mathematically complex process to separate the recorded signal into independent sources that we can make sense of. So an example of this is on the bottom left. And then once we do that, we look at it amongst the bands. So on the bottom right is a typical event-related spectral perturbation plot that most people who do independent component analysis and source vocalization tend to look at. So different regions of the brain that this paper was interested in was the occipital cortex, which is visual processing, the posterior parietal, which integrates sensory information to guide actions, the anterior parietal, which is processing tactile sensations and proprioception, the sensory motor, which is motor functions, supplementary motor, which is planning, initiating, sequencing voluntary complex movements, and the anterior cingulate, which is error detection, decision-making, and attention. And so just a little bit more on the background. So I'm going to talk about like an increase in power or a decrease in power or synchronization and desynchronization. So synchronization, kind of like, this is how my PI explained it to me using the SpongeBob meme, so I thought it was kind of funny, but kind of when all the neurons are kind of like focused on the same task or in sync. So neurons oscillate, the potential oscillates. And so when these are in sync, that's when there's an increase in power. And then when there's a decrease in power, it's not necessarily a bad thing or a good thing. It just means that neurons are maybe focused on doing other things. So they're not all focused on the same thing. So when you have your eyes closed, your occipital cortex actually has a very large increase in power because all of your neurons, they're doing the same thing because you're seeing nothing. So the research question and hypothesis of this paper is, how does cortical activity differ in response to visual versus physical balance perturbations during standing and walking? And they hypothesized that visual perturbations and physical perturbations will increase theta power and decrease beta power, indicating detection of perturbed balance and decreased motor inhibition. So a little bit about the experimental design. They had 30 participants who completed a physical pull and visual perturbations while standing and walking. For the walking trials, they walked on a treadmill on a balance beam, heel to toe. And then during standing trials, they just stood heel to toe. They were asked to cross their arms and only use side-to-side hip movement for balance to reduce the variability and to increase the difficulty of the task. And the physical pull perturbation, the participants were pulled by a cable at 90 degrees for 1 second. So it was a quick pull and then a release. And then the visual rotation, they were wearing VR goggles, and the scene in front of them was rotated 20 degrees clockwise or counterclockwise for half a second. And so all the participants completed 4 total trials and each one was 10 minutes long and consisted of 150 total perturbations. So participant 1 might have completed standing physical pull for 10 minutes where there were 150 total perturbations, and then would complete maybe walking visual rotation. And the order of the perturbation type was randomized, and then the order of the actual perturbations was predefined in pseudo-random sequences. So as I said earlier, EEG analysis is very complex and lengthy. And there's no gold standard processing pipeline, but there are generally similar steps or things that kind of all EEG researchers that do this type of analysis complete. So they used EEG Lab, which is a widely used MATLAB toolbox for EEG analysis. And basically, initially they pre-processed all of the data. So they removed like electrical noise. They filtered their data. They removed bad channels. So in EEG, sometimes you use conductive gel, and sometimes hair gets in the way. So that channel may not have a good connection. So that might be a bad channel that you would get rid of so that it doesn't, I guess, influence the rest of your data. And then once you kind of initially process your data and get to channels that you think are, I guess, have solid connections, are not motion artifact, they're not eye blinks, it's not muscle activity. Then you get to independent component analysis, where you can kind of fully separate what is true brain activity, and then dipole fitting. And so each independent component was fit into an equivalent dipole to identify components in plausible cortical regions. So kind of look